Welcome to Lab 10. This week we're going to be talking about one-way ANOVAs as well as how to run post-hoc tests using Fisher's LSD to determine whether there are differences between group means within a study that has more than two groups. First, we're going to be talking about the example we'll be covering in class about guilty ratings in 3 different conditions. In this example, we are looking at a study where social psychologists are curious whether or not they can affect juries' perceptions of the guilt or innocence of a hypothetical subject. In one group, the jurors are told that the subject or the defendant has a criminal record. In the other, they are told that the defendant has a clean record, and in the third, they have no information. The idea is to find out whether or not knowing someone's background sways future decisions and future perceptions of an individual's culpability. So in this study, we could run a simple t-test in between criminal and clean record. We could run it between clean and no information or criminal and no information, so looking at the 3 possible pairwise connections. But as we've learned in class, this would result in significant added error, that each one of these analyses has about a 5% chance of being incorrect or showing some statistical significance, even if there was no actual significance in the real world. So showing some difference, even if there was no difference in the real world. So because of this, we don't want to run multiple tests. We instead want to run them simultaneously, accounting for the potential error so that we minimize that error. So we are going to have to run a one-way ANOVA in this case that simultaneously compares the means of all 3 groups. Now, in using PSPP for a one-way ANOVA, we're going to have to think similarly to how we did in the independent means t-test on how do we organize the data. We'll see that the data from in class has 3 groups: the criminal record, the clean record, and the no information. And just like when we saw with an independent samples t-test, we have a subject number associated with each of these groups. So subjects 1 through 5 were in the criminal record, 6 through 10 were in the clean record, and 11 through 15 were in the no information group. But of course here it looks like we have 6 different variables. However, 3 of them overlap as the subject number, and 3 of them are not actually variables, but levels of the actual independent variable. In fact, here we have it, that those scores we have in the criminal record group, clean record group, and no information group are actually not from the independent variable, but are related to the dependent variable. They are the numbers corresponding to the ratings of innocence or guilt. So we want to make sure that we have a single variable that covers all of the subject numbers, a single variable that covers all of the dependent variable, that guilt, innocence, as well as a single variable that indicates the levels of the independent variable. In this case, what information was given about the defendant. We have 3 of those levels, as we will see: the criminal record, the clean record, and the no information. So in PSPP, we need to reorganize our data. So we'll see here in the PSPP, we have one column associated with subject number, where we have 1 through 15. In the second column, we have the guilt ratings, that dependent variable, where we have all of the scores associated with the subject number. And then finally, we're going to add in a new variable called group. In this case, we're going to indicate whether the individual has a criminal record, or whether the participant was told that the defendant has a criminal record, a clean record, or was given no information. Each of the variables has its own column, and then within those variables there are different levels. In the group, the levels are of a nominal category. In the guilty ratings in the dependent variable, that is a continuous variable, and so we have possible scores of 1 through 10. So let's go ahead and open up Lab 10 data. Here you'll see 3 variables: the subject number, the ratings of whether the participant is guilty or the subject is guilty or innocent, and the group variable, the independent variable that includes 3 values. Those values are going to be the criminal record group, the clean record group, and the no information group. These are labeled as 1, 2, and 3 respectively. But again, these value labels could be anything. They could be 9 or 73 or 562. As long as they are unique, they will be okay. So we have the three conditions, three grouping variables. And if we go to our data view, we will now see our data listed out with all of the 15 subjects, each of the ratings that those participants gave to the participant they viewed, as well as the condition that they were in, represented by those three values. We can toggle to the labels where we see criminal record, clean record, no information. So the first thing we might want to do is see our descriptive statistics for the group, for our metric of guilt ratings. So we could go to descriptives, move over our guilt rating. We're going to keep it to just the mean and standard deviation. Click OK. And when we open up our output, we'll see that among the 15 participants in our study, the average rating of guiltiness was a 5.6 with a standard deviation of 2.69. We have our standard syntax of descriptives, our variables of guilt rating, and the statistics of the mean and standard deviation. But we know that we have three different groups, so this overall descriptive statistic is not going to be as useful to us. We instead want to see each of the groups individually. So we would go to Data, Split File, because we want to see we want to split our file based on which group and condition they're in. So we're going to organize by the groups. Click OK. We now have, if we look at our syntax, we will see that it sorted the cases based on group, and it split our file and separated it by group. So that now any output we get is going to give us individual output for each, whether people scored a 1, a 2, or a 3 on their group variable. So if we go again to Analyze, Descriptive Statistics, and Descriptives, and we still have the guilty rating with the mean and standard deviation listed, click OK. And this time we're going to get the descriptive statistics based on the three groups. So first group, the criminal record group, that was a score of 1, a value of 1 in this variable. We have 5 participants and a mean score of 8 with a standard deviation of 2.12. For the clean record, a mean of 4. For the no information, a mean of 4.8. And these will match the statistics that you will get by yourself when we calculate the average of those 5 individuals. All right, so we now have seen the descriptives, but we want to know, does this mean of 8 differ from a mean of 4? And does the mean of 4 differ from a mean of 4.8? Are there any differences between these three groups? Now we could run a t-test where we just compare the criminal record to the clean record group, and we might find something significant, but that would be ignoring the no information group. Or we could run between the criminal record and the no information group, but that would ignore the clean record group. So we want to make sure that when we are doing this analysis, we're including all three groups and all of the variation among all three groups simultaneously. So let's go back to our data file. And let's make sure we turn off our split file. We want to undo that. Okay, do not create those groups so that any data we get is going to look at everything at the same time. And this time we're going to analyze our data to see are the means different by going to Analyze, Compare Means, and a one-way ANOVA. This will open a pop-up that's going to have on the left-hand side all of our variables. And in the middle, we're going to have 2 cells that are available for our dependent variables and our factor. You'll recall from our lecture that factor is a code word for independent variable. So we think about what is the variable that is having an effect, our independent variable. That's going to be our group membership, which condition they are in. So we'll move that over to the factor. Our dependent variable is going to be those guilty ratings. That's the outcome we care about. We think that people's rating of innocent or guilt is going to be dependent on whether they read a criminal record or a clean record. So we have our dependent variable, we have our factors, and we could click OK, but we also might want to know the descriptives, the details of each of those groups, and the total mean and standard deviations. So let's click this descriptives, and now we'll go OK. So scrolling down in our output, here we have the syntax for this one-way ANOVA. It's going to use the code one-way, not ANOVA. In this case, it's one-way. It's going to declare our variables, the dependent variable by the independent variable. So dependent first, independent second. And then here we have a line asking specifically to checkbox for those descriptives. We're then going to get two tables. The first is those special statistics that we asked for. This wouldn't appear if you had not checked that box. This is going to give us our sample size for each of the groups as well as the total. And here you'll see the means for those respective groups. So again, we see that 5.6 and the 2.69 for our overall, which if we scroll back up, we'll see was when we had not split the file. There's that 5.6 and 2.69. But we also see our individual group means, that 4, the 8, 4, 4.8. We also are going to get a little bit more information here with our confidence intervals around the mean of each of these groups. So of 5 participants, if we got any 5 participants, we are 95% confident that we would have gotten a mean in this criminal record group between a 5.37 and a 10.63. In the clean record group, we would have gotten a mean between a 1.22 and a 6.78. And in the no information group, we're guessing we are 95% confident we would have gotten a mean between a 2.11 and a 7.49. These confidence intervals are calculated based on this mean and then the t value times that standard error, exactly as you would calculate a confidence interval in any t-test. Right. So those are the descriptives that we asked for, and we would look at this and see that the criminal record looks like it's higher than the no information or the clean record, but we don't actually know yet. We don't know if this gap of 4 is significant. So what we'll do next is look at this ANOVA table, and this is the table that's going to have all of the statistics that we're going to need for this ANOVA. We have seen this called a source table when we've been doing it in class. So there's lots of numbers to keep track in an ANOVA, but we're going to see them all listed out here. So the first thing we're going to see, the first column, is going to be those sums of squares. You'll recall that the sum of squares is the equivalent of that sum of a score minus the mean squared, and then you sum all of those up. And so here we have our between groups. This is the amount of differences that occurred, the squared number of differences, or the sum of the squared differences between each of the conditions. So between the mean of each group and the grand mean. The within groups, this is going to be the sum of all of the individual scores subtracted from their respective group means. And our total is going to be each individual score subtracted from the grand mean. You'll also see that this 44.8 and 56.8 add up to the 101.60, so obviously the math is correct there. We'll also get our degrees of freedom, which we know as the k minus 1, the n total minus k, and the n total minus 1. And then it's going to do the math where it just divides laterally. So 44.8 divided by 2 is that 22.4. The 56.8 divided by 12 is that 4.73. And then our final F statistic is going to be the mean squared between, that 22.4, divided by the mean squared within, that 4.73, which will give us an F statistic of 4.73. And we look at our significance, our p-value, and see that it is 0.03, so that is less than a 0.05. So we would reject the null hypothesis and say that there is, in fact, a difference here. Of course, though, just because there's a difference between these means doesn't tell us in an ANOVA which means are higher. So we don't know that all 3 of these means are different from each other significantly. We just know that at least one of these means is different from the others. So eyeballing it, we might have an idea that this criminal record group has a higher mean than the clean record group, but is it also significantly higher than the no information group? And is the clean record group significantly different from the no information group? We don't know yet. In order to answer that question, we're going to have to run our post hoc analyses. Specifically, we're going to run the Fisher's least significant differences test. That's pretty easy to do in PSPP. We simply go to Analyze, Compare Means in One-Way ANOVA, just as we did before. But this time, before we click OK, we're going to go to this button for post hocs. So all of the post hoc afterwards analyses we're going to do here. And it's going to give us a number of different options. The most standard ones are going to be the Fisher's LSD, which we're going to do today. But you might also see a lot of references in text and in other statistics books to Tukey's HSD, which is very similar. It just uses a slightly different variability. But today we're going to use the Fisher's LSD. We click Continue. Nothing seems to have changed, but it is now included. We click OK. And we'll go again to our output, and we get the same descriptives. Oh, scroll down. We get the same descriptives here. We get the same ANOVA source table, but this time we get our multiple comparisons. So this multiple comparisons group is going to show us each pairwise combination. So it's going to take one of the groups and compare it with one of the others. So here we have the criminal record compared with the clean record. It's going to give us our mean difference, our group 1 labeled by an I, and our group 2 labeled by a J. It's going to compare them and say that they have a difference of 4. And then it's going to do a t-test, a normal t-test with this standard error, and calculate a significance. This significance is used just like any other alpha, that it is less than 0.05 is significant. So we are going to reject the null hypothesis that these two groups are similar to each other, and instead say that they are significantly different. So, and you'll see that this criminal record group has a mean of 4, and this clean record group has the mean of, the criminal record group has a mean of 8, and the clean record group has a mean of 4. So that difference is that 4. So this 4 is large enough for us to say is important. We then look at our criminal record group compared to our no information group. We see they have a difference of 3.2. That's the 8 minus the 4.8. And we find that this is also less than 0.05, so it is also significant. We can say that the criminal record group mean is higher. They are more guilty than those who got no information. And then we can also look down here at our clean record group compared to our criminal record group. And we see a negative 4, and it's significant. But you'll notice that this line, the clean compared to criminal, is exactly the same as the criminal compared to clean, except reverse. This is similar to how we have dealt with it in independent means t-tests and dependent means, that the order that you compare them will change whether it is positive or negative, but the significance is still the same. The same goes for criminal record and no information group. We could come down here to the no information group compared to a criminal record group and see that negative 3.2, still the same p-value. It is still just as rare to get this result. So we've seen 2 of the pairwise combinations, but we have one last one, and that's between our clean record group and our no information group, between the score of 4 and the mean score of 4.8. So we would look either on this combination or on this combination in no information with clean, and either one of those will give us a plus or minus of the 0.80, a difference of 0.8. And we can see here that this significance is now very not significant. It is a 0.572. What are we doing here? So that small difference between these two is not big enough for us to say that there's any difference. So how do we report this? Well, first we would want to make sure that we report the overall model. The overall, is there a difference between all 3 of our variables simultaneously? And we would say, yes, at least one of these means is different, that the independent variable of condition matters for whether people get a guilty or innocent rating. But where does that difference lie? Well, then we follow up and say that a post hoc Fisher's LSD test showed us that those who viewed a criminal record rated subjects as significantly more guilty than either the clean record group or the no information group, but there was no significant difference between the clean record group and the no information group. So what we've done here is give the model, as well as give each pairwise comparison letting the reader know exactly where that difference lied. The last thing I want to point out is the standard error column. You'll notice that these standard errors are all the same. And that's because in a Fisher's LSD, this standard error is represented by that special equation of the square root of the mean squared within, ms within, times the sum of 1 over n plus 1 over n2. 1 over n1 plus 1 over n2. So that's the equation for standard error. In our case, the n's for all of the groups of 5 were consistent, and the mean squared doesn't change. So all of our denominators in our LSD equation are going to be the same, that 1.38, which again we will see in our calculations in class. And finally, just to finish up on our syntax, we'll see that nothing has changed in this one-way ANOVA syntax. We still have the dependent variable by the independent variable. We have our statistics listed out, represented in this descriptives table. The only thing we've added is this post hoc keyword, as well as the special keyword for the type of post hoc we are running, which in this case is LSD. That's all you need to add. And that's it. That's how to run a one-way ANOVA.